August 1943. A secret specification from the United States Army Air Forces lands on the desk of Republic Aviation's chief designer. The customer's requirements brutally violate the basic laws of physics of the time. The military needs a 4-engine aerial reconnaissance aircraft capable of loitering for hours over the Japanese Empire at an altitude of 40,000 feet while making continuous photographic passes. But the main requirement is speed. The customer demands a cruising speed of 400 miles per hour and a maximum speed above 466 miles per hour. At that time, the best single-engine piston fighters began to shake apart from vibration or fall into spins when attempting to hold such a pace in the thin air of the stratosphere. Here, however, the subject was a massive, all-metal Leviathan with a wingspan of almost 131 feet and a maximum takeoff weight of 101,400 pounds. This is the equivalent of the mass of 15 medium Sherman tanks that had to be accelerated to bullet speed using only pistons, aviation gasoline, and propellers. Any engine vibration would turn the long-focus camera images into a blur, so the structure of the frames and stringers demanded absolute monolithic rigidity. Alexander Kartveli, the aerodynamic genius and creator of the brutal P-47 Thunderbolt ground attack aircraft, understood perfectly that the old school of aircraft design was powerless here. Engineering had run into a solid thermal wall. To move 46 tons of metal at 750 miles per hour required enormous thrust. Thrust demanded gigantic piston engines, and gigantic radial engines have a huge frontal area. They create air resistance comparable to trying to drag an open parachute through a concrete wall. To overcome that resistance, still more power is needed, which means still larger cylinders, increased mass, and still greater frontal resistance. It was an engineering dead end. A mathematical loop in which the laws of thermodynamics and aerodynamics devoured each other. The traditional approach, with wide, barrel-shaped nacelles protruding from the wing, guaranteed failure already at the stage of the first drawings. Every extra inch of projecting aluminum at 700 miles per hour consumed hundreds of gallons of high-octane fuel and irreversibly stole precious miles of range. The project received the designation XF-12 Rainbow. Financing was opened immediately. The initiator of the creation of this machine was Colonel Elliott Roosevelt, son of the sitting President of the United States of America. Money had no meaning. The only thing that mattered was the ability to photograph enemy factories with impunity from an altitude beyond the reach of anti-aircraft artillery. Kartveli resorted to absolute radicalism. He decided to deceive the oncoming flow by hiding the most massive power plant of the decade inside an aerodynamic duct of ideal shape. The heart of the machine was to be 4 radial 28-cylinder monsters, Pratt & Whitney R4360-31 Wasp Major. In total, that meant 112 cylinders, 224 valves, and 224 spark plugs pounding furiously inside tight duralumin shells. This was not merely a vehicle. It was a precision clockwork mechanism weighing 45 tons, where clearances were measured in fractions of a millimeter, and the oil pressure in the lines was ready to burst the seals at the slightest error by the designers. The XF-12 Rainbow would become a true masterpiece of the piston era, an aircraft whose fuselage profile sliced through the air with the lowest drag coefficient in its enormous class. It would prove its worth in practice by flying across the entire North American continent from coast to coast in less than 7 hours, leaving in its cassettes a perfect continuous photographic strip 390 miles wide. But why did a project with unlimited administrative resources, an aircraft that broke the speed records of its age and whose drawings seemed flawless, never produce a single production aircraft? why was its only surviving prototype ultimately ignominiously cut up for scrap at the Aberdeen Proving Ground? The answer lies neither in conspiracy theories nor in fatal design blindness. A brilliant mathematical calculation was shattered by harsh economics, the change of global eras, and one carefully concealed engineering compromise that turned every flight of this perfect airplane into a gamble on the edge of a massive thermal explosion. Alexander Cotvelli understood perfectly that to achieve a cruising speed of 400 miles per hour at an altitude of 40,000 feet, ordinary mechanical power would be absolutely insufficient. The heart of the reconnaissance machine became 4 radial piston engines, Pratt & Whitney R4360-31 Wasp Major. This was the physical limit, the absolute ceiling of the evolution of piston aviation in the United States of America. Each such aircraft engine weighed 3,620 pounds dry, equal to the mass of a full-size Army truck made exclusively of high-alloy forged steel, duralumin, and combustible magnesium. Inside each crankcase were densely hidden 28 cylinders arranged in 4 rows of 7, with offset so as to capture at least some of the oncoming air. 3,200 horsepower on each shaft gave 12,800 horsepower of total power at takeoff rating. To grasp this mathematical scale, imagine the power of the power plant of a heavy diesel locomotive that Republic Aviation Corporation engineers managed to pack into 4 metal ducts suspended from the wing. This mechanical leviathan consumed 115-octane aviation gasoline at a frightening rate, requiring thousands of gallons of high-octane fuel merely to maintain basic operating RPM. Inside the 4 engines, a total of 896 spark plugs worked, while 448 valves opened and closed at a brutal frequency, creating a deafening symphony of controlled explosions. Vibration from this colossal mass of rotating metal would guaranteedly have torn standard longerons to pieces, so the engine mounts were designed with unprecedented reserves of structural strength. The engineers employed massive damping assemblies of dense synthetic rubber and steel, capable of absorbing 1,000 Hz oscillations without transmitting destructive resonance into the aluminum fuselage frame. Yet the principal engineering problem lay not in the generation of pure power, but in frontal drag. A classic air-cooled radial engine requires a wide, blunt forward section so that a massive stream of oncoming air can cool the glowing cylinder barrels. Had the designers installed on the wings 4 standard barrel-shaped nacelles from the heavy bomber Boeing B-50 Superfortress, equipped with exactly the same engines, aerodynamic drag would immediately have consumed more than 1/3 of the power being produced. With such an arrangement, the aircraft's maximum speed would forever have been stuck at 342 miles per hour. Cotvelli made a technical decision that grossly violated all the unwritten rules of classic engine design. He designed for the XF-12 rainbow nacelles of incredible, almost pencil-thin narrowness. Each of the 4 nacelles had a length equal to that of the fuselage of a full-size, single-engine Republic P-47 Thunderbolt fighter. These were absolutely smooth, elongated aluminum torpedoes, completely devoid of the usual wide, circular air intakes at the front. To supply these huge engines with oxygen for the fuel mixture and air for cooling, the designers cut massive slots into the leading edge of the wing itself, between the fuselage and the inboard engines, and also between the inboard and outboard nacelles. Air at 600 kilometers per hour and enormous pressure rushed into these narrow openings, passed through a complex system of internal labyrinthine channels inside the wing consoles, and only then was fed to the glowing cylinders. This radical solution made it possible to create an aircraft with the lowest frontal drag coefficient in the entire history of 4-engine piston aviation. The heavy 46-ton machine literally sliced through the dense layers of the atmosphere without creating a destructive wall of compressed air ahead of it, saving precious gallons of gasoline on every kilometer of the route. The engineering of this aircraft concealed one more hidden technical trick that forever turned it from an ordinary piston reconnaissance plane into a unique hybrid machine with the beginnings of jet technology. Exhaust gases from 112 enormous cylinders, heated to a temperature of almost 1,000 degrees Celsius, were not simply dumped overboard through short exhaust stubs, as was done on older bombers. Each engine was equipped with two massive General Electric turbo superchargers hidden deep in the aft section of the nacelle. After passing through the turbine blades, which under enormous pressure forced dense air into the carburetors for stable engine operation in the thin stratosphere, this superheated gas flow was directed through long, heat-resistant ducts straight to the very end of the aft section of each nacelle. There, the steel pipes gradually narrowed, forming true profiled jet nozzles. The expanding gases burst outward at enormous speed, generating stiff, tangible jet thrust. At cruising altitude, each of the four piston engines produced roughly 250 horsepower of equivalent jet thrust, solely from the kinetic energy of the exhaust. In total, this delivered exactly 1,000 horsepower of pure jet energy that constantly pushed the heavy reconnaissance aircraft forward at no cost, without requiring the burning of a single extra drop of high-octane fuel from the wing tanks. This was a genuine masterpiece of thermodynamic efficiency, in which destructive thermal energy that normally escaped into the atmosphere as useless heat and loud popping noise was converted into a direct thrust vector, adding dozens of precious miles per hour to the aircraft's maximum speed. However, the ruthless laws of thermodynamics never forgive engineers who attempt to cheat them with elegant drawings. The brilliant aerodynamics concealed a fatal technical flaw that became a true time bomb for the entire project. Even under ideal laboratory conditions on the test stand, the 28-cylinder Wasp Major engine was notorious for its tendency toward rapid and uncontrolled overheating. The cylinders stood in 4 rows, packed tightly, one behind another, and while the first row received fresh, icy, stratospheric air, the second, third, and especially the fourth rows received only superheated airflow that had completely lost its physical ability to remove excess heat from the metal. By packing these colossal thermodynamic furnaces into narrow, form-fitting duralumin tubes for the sake of ideal speed, the designers deprived the metal of its last chance at normal cooling. Inside the nacelles, there was simply no physical volume of space for the free circulation of air needed to carry away the enormous quantity of thermal energy from the cylinder barrels. The airflow that struggled through the narrow intakes in the wing desperately tried to cool the rear rows of the engine, but its density and velocity were catastrophically insufficient. The temperature of the rear cylinder heads regularly exceeded every conceivable operational limit set by the designers. The expensive cylinder metal began to expand unevenly. Thermal clearances in the valve mechanisms disappeared, and hundreds of gallons of aviation oil inside the lubrication system began to lose viscosity at a rapid rate. Oil turned into a useless liquid substance incapable of preventing dry friction of parts, and the risk of sudden ignition of gasoline vapors inside the cramped engine compartment hung invisibly over the crew every second of flight. This was an absolutely cold, cynical deal with physics. To fly at the speed of a jet interceptor, the 45-ton reconnaissance machine had to constantly balance on the brink of total thermal melting of its own power plants. Every extended test flight became an exhausting task of manually controlling cowl flaps, monitoring oil pressure surges, and adjusting propeller pitch. The slightest miscalculation by the pilot, or the ordinary mechanical failure of a single air valve, guaranteed a massive fire at an altitude of 12 kilometers, leaving the military crew alone with a raging magnesium blaze that could not be extinguished even by the strongest oncoming airflow. February 4th, 1946, became the day of a harsh collision between ideal aerodynamic drawings and harsh thermodynamic reality. On that day, the first flying prototype with serial number 44-91002 lifted off the concrete runway of the test base. The 7-man military crew, including Chief Test Pilot Oscar Lowry Brabham, found itself locked inside a sealed aluminum tube at an altitude of 40,000 feet. On paper, and in reports to the general staff, the flight looked like an absolute triumph. The airspeed indicators in the cockpit displayed fantastic numbers. The heavy 46-ton machine flew level, slicing through the cold stratospheric air without the slightest sign of flutter or loss of control. But behind the instrument panel, an unrelenting, exhausting battle with physics was unfolding. Thermocouples on the cylinder heads of the 28 cylinders in each of the 4 engines registered constant, uncontrolled temperature spikes. The pilots had to juggle the operating modes of the massive General Electric turbosuperchargers every minute, adjust the enrichment of the high-octane fuel mixture, and change the pitch of the giant 4-blade propellers to prevent the exhaust valves from burning out. The air intakes cut into the leading edge of the wing, so elegantly designed by Alexander Cardvelli to completely eliminate the frontal drag of the nacelles, greedily gulped the thin air. But the long, geometrically complex curved channels inside the duralumin consoles slowed this airflow, consuming critically important aerodynamic pressure. Republic Aviation Corporation engineers on the ground studied the telemetry with growing horror. The rear rows of cylinders of the WASP major radial engines were literally suffocating in their own superheated oil, whose temperature exceeded 248 degrees Fahrenheit, turning the lubricant into useless liquid water. Parallel to the secret military tests, the corporation launched a large-scale marketing campaign for a civil version of the aircraft under the internal designation RC-2. This was an absolutely cynical attempt to sell the thermodynamic monster to commercial airlines in order to recoup the colossal development costs. The project was redesigned to accommodate 46 passengers, who were promised an unprecedented level of luxury on transatlantic flights between New York and European capitals. Advertising booklets printed on expensive glossy paper described a pressurized passenger cabin finished in fire-resistant veneer of genuine Honduran mahogany with a total weight of 397 pounds. Clients were offered deep seats upholstered in thick calfskin leather, a full onboard galley with powerful electric ovens, and a bar counter of solid polished aluminum. The projected one-way ticket price exceeded the average monthly wage of a skilled factory worker in the United States of America by a factor of 3. The civil version was to cross the Atlantic Ocean hundreds of miles per hour faster than any existing competitors, avoiding dangerous weather turbulence thanks to its colossal cruising altitude of 40,000 feet. But the marketers and designers carefully concealed from investors a fundamental operational flaw. To service the 4 enormous Pratt & Whitney engines packed tightly inside narrow torpedo-shaped shells, aviation mechanics required hundreds of exhausting man-hours after every long flight. Access to the spark plugs and lower rows of cylinders was physically impossible without completely removing the outer load-bearing panels of the nacelle. In commercial aviation, where margins are measured in fractions of a cent per mile, an airplane makes money only when it is in the air. The necessity of keeping the 46-ton machine in a warm hangar for 2 full days for the routine replacement of burned-out piston rings, adjustment of clearances, and inspection of 448 valves meant a direct path to financial bankruptcy for any airline. The commercial sector demanded ironclad reliability and dull predictability, not a temperamental military prototype prone to sudden spontaneous combustion from the slightest disruption of temperature balance in the crankcase. The point of no return for the first aircraft built was not a fiery catastrophe in the stratosphere from overheating, which all the engineers subconsciously expected, but a banal, brutal hydraulic failure. July 10, 1947, wiped out months of the most complex technical refinements and millions of dollars spent. During another test flight, the first prototype was preparing for a routine landing at the base. Pilot Oscar Lowry Brabham flipped the landing gear switch to the down position with a practiced motion. The left main gear and the massive nose strut locked into place with a heavy metallic thud, securing the powerful hydraulic cylinders in the extended position. But the right main gear, a gigantic steel strut weighing more than 1,320 pounds and fitted with two enormous rubber tires, remained jammed inside the nacelle bay. The door latch mechanism had seized because of a hidden fatigue defect in the metal. Tons of special red hydraulic fluid, pumped by the aircraft's pumps at an enormous working pressure of 3,000 pounds per square inch, could not overcome the resistance of the deformed piece of hardened steel. Further desperate attempts by the pilot to shake the stuck gear loose with sharp banks and high-G maneuvers produced no result. The fuel gauges inexorably approached zero, while the four huge engines continued to devour the remaining gasoline. The miracle of aeronautical engineering, created for impunity dominance in the sky over the territory of a potential enemy, proved completely helpless before a piece of jammed metal costing $75. The pilot had no choice but to land the airplane on its belly. It was a mathematically calculated, ice-cold decision based on safety protocols. Brabham shut off the supply of high-octane aviation gasoline to the right-hand engines and closed the lines to minimize the risk of a large-scale volumetric detonation of the wing tanks upon contact with the concrete and hard ground. The airplane touched down on the surface of the auxiliary dirt strip at a speed of about 118 miles per hour. Thousands of steel rivets on the lower part of the fuselage were instantly sheared off by friction against the hard, compacted earth. The smooth, aerodynamic skin of 24ST aluminum alloy 2.4 millimeters thick began to crumple like an accordion, absorbing the colossal kinetic energy of the sliding impact. The 45-ton mass continued by inertia for hundreds of yards, stripping away the lower panels, tearing cable runs, and breaking frames with a deafening screech of rending metal. The temperature from the friction of the skin against the ground locally reached 932 degrees Fahrenheit, threatening to ignite the remaining aviation oil in the damaged ventral lines. When the mangled airframe finally came to a stop, raising a dense, impenetrable cloud of acrid dust, the entire crew immediately evacuated through the emergency hatches. There were no human casualties, and no fatal fuel fire. Cartvelli's monolithic engineering design brilliantly withstood the monstrous mechanical stress, preserving the integrity of the pressurized passenger capsule. However, the preliminary technical inspection conducted by the military commission right at the accident site delivered an immediate and harsh economic verdict on the entire project. The hard landing caused irreversible, catastrophic deformation of the primary load-bearing structure. The central wing carry-through box was displaced relative to its axis, and the long cigar-shaped fuselage sustained a deep structural fracture that was absolutely impossible to repair by simply replacing bent stringers. Restoring the first aircraft would require the construction of completely new steel jigs, complete disassembly of the airframe down to the last rivet, and the fabrication of new key load-bearing elements from scratch. Pentagon military financiers, armed with slide rules, quickly calculated the final cost of repairs. The figures proved astronomical and exceeded the original estimate for building a new aircraft. The XF-12 Rainbow program budget was already bursting at the seams because of constant expensive modifications to the cooling system of the temperamental engines. Restoration of the wrecked first prototype was officially declared economically inexpedient. The magnificent machine, which only that morning had been regarded as the unsurpassed pinnacle of world piston-powered aviation, was instantly stripped of its airworthy status. It was ruthlessly cannibalized for spare parts, cynically stripped of its hydraulic pumps, expensive high-altitude avionics, and surviving left-side Pratt & Whitney engines to supply the second prototype, still on the assembly jigs with scarce replacement components. This accident did not kill the strategic reconnaissance concept on the same day, but it became the very first cold warning of an approaching failure. It clearly demonstrated to the United States Army Air Force's General Staff how fragile, temperamental, and financially unsustainable this ambitious Leviathan was under real-world field conditions. The second aircraft built, with the tail number 44-91003, took to the air on August 12, 1947. Republic Aviation Corporation engineers had corrected some of the previous critical errors by slightly modifying the cooling systems, but the fundamental physical conflict between the narrow aerodynamics and the boiling cylinders remained unresolved. Nevertheless, the aircraft was obliged to prove its absolute viability to the customer. On September 1, 1948, this duralumin Leviathan performed a flight that entered military history under the codename Operation Birdseye. The machine lifted heavily from the warm concrete runway of Muroc Air Base in California and took a precise course toward the East Coast. At a cruising altitude of 40,000 feet, where the outside temperature remained steady at -69 degrees Fahrenheit, the crew activated the synchronized bank of heavy, long-focus cameras. Flying at enormous speed, the aircraft crossed the entire North American continent and landed at Mitchell Air Base in New York exactly 6 hours and 55 minutes later. During that time, the precision clockwork mechanisms of the cameras recorded a continuous photographic strip 390 miles wide. No other heavy aircraft in the world at that time could accomplish such a task at such speed and at such altitude. For the first time in aviation history, military cartographers obtained a detailed, seamless photograph of the entire territory of the United States of America from coast to coast in a single flight. This was an absolute, unqualified triumph of piston engineering, proving that Alexander Kartvel's concept worked not only on drawing boards, but also in the icy vacuum of the stratosphere. During this flight, the 4 enormous Wasp major engines burned thousands of gallons of high-octane gasoline, while their massive turbo-superchargers continuously generated that very same hidden jet thrust, adding life-saving knots of speed to the heavy reconnaissance aircraft. It seemed that boundless financial prospects now opened before the corporation, and that a multi-million-dollar production contract already lay on a polished desk in the Pentagon. Yet the final verdict on this engineering marvel was delivered not by structural fatigue of the metal, not by microcracks in the frames, and not by the capricious thermodynamics of the 28-cylinder engines, but by the ruthless, emotionless mathematics of technological progress. By the end of 1948, the global paradigm of aerial warfare had changed forever. While the engineers and mechanics of Republic Aviation Corporation spent days and nights fussing over thousands of valves, spark plugs, and the intricate oil lines of the piston-powered XF-12 Rainbow, their competitors at Boeing had already flown the heavy jet bomber XB-47 Stratojet. Turbojet engines burned the old school of engineering to ashes. They were incredibly thirsty, consuming aviation kerosene by the ton, yet their design contained dozens of times fewer moving parts. There were no heavy forged pistons, complex carburetors, temperamental ignition systems, or the eternal insoluble problem of uneven cooling of 4 rows of glowing cylinders. Cold air was simply sucked into a huge axial compressor, mixed with fuel, and ignited, delivering clean, continuous, monstrous thrust. The jet engine was technologically simpler, more reliable, and, most importantly, It produced linear speeds utterly unattainable by propellers, whose blade tips rapidly lost aerodynamic efficiency as they approached the sound barrier. 750 kilometers per hour, which had seemed an unattainable fantasy for a heavy piston airplane, suddenly became the baseline cruising speed for early jet machines. Sending a piston-powered reconnaissance aircraft into the airspace of a potential adversary, already openly identified in secret documents as the Soviet Union, had become absolute tactical suicide. The appearance of early jet interceptors, such as the Soviet MiG-15, armed with heavy 37mm aircraft cannon, instantly turned the enormous 45-ton Republic XF-12 Rainbow into a slow, sluggish, and incredibly expensive target. Maximum speed no longer protected the airframe from destruction, and an operating altitude of 40,000 feet ceased to be a 100% guarantee of safety from aimed anti-aircraft fire. Military analysts needed only a few closed sessions to put a permanent end to the program that had consumed millions of dollars from the federal budget. The choice was made in favor of the new jet reconnaissance aircraft, RB-45 Tornado and RB-47 Stratojet. They flew much higher, flew faster, and did not require the maintenance of an entire army of specialist mechanics for the daily, multi-hour servicing of just one temperamental power plant. The history of this ideal piston-powered aircraft ended with the maximum severity characteristic of the pragmatic American military machine. The central intrigue built into the design phase resolved itself in the most cynical and paradoxical way. The machine, created with an unlimited budget, and for which brilliant engineers had deliberately broken all the basic rules of classical aerodynamics, turned out to be needed by absolutely no one. The civilian commercial sector categorically rejected it because of the monstrous cost of ground maintenance for the Pratt & Whitney engines, while military generals wrote it off because of total obsolescence in the face of the approaching jet revolution. The only surviving prototype, tail number 44-91003, was used for several more years as a flying laboratory for testing new photographic equipment. But by 1952, the basic cost of maintaining the airworthiness of this extraordinarily complex 45-ton mechanism had critically exceeded any reasonable value of the test data obtained. The aircraft was permanently stripped of airworthy status and transferred to the books of the Aberdeen Proving Ground. In this cold place, there was no room for aviation sentiment. The machine that only 4 years earlier had set a transcontinental speed record and flown over the entire country was routinely towed by heavy military tractors onto an open firing range. The perfect aerodynamic contours, the optimized wing profile that had permanently reduced drag to a historic minimum, and the pressurized fuselage, capable of withstanding enormous internal air pressure, became nothing more than a static target for testing new, high-explosive fragmentation army munitions. The 24ST aluminum alloy, which for years had endured the icy, stratospheric cold and the most brutal aerodynamic turbulence, was methodically torn to shreds by hot shrapnel and heavy machine gun bursts. What remained of the beautiful, all-metal airframe after the ballistic tests were completed, the range workers simply cut with acetylene torches into shapeless pieces of dirty scrap and immediately sent to industrial smelting furnaces. The XF-12 Rainbow became a monumental memorial to the greatest engineering dead end of the 20th century. It was the true pinnacle of technical evolution, the most perfect and flawless creation of the departing piston era, which fatally arrived one technological step too late for its rendezvous with world history. This project forever proved that in the ruthless aviation business, even the most brilliant and meticulously developed drawing is not worth a cent if it is printed on yesterday's paper. The complete collapse of the XF-12 Rainbow program left behind not only mountains of twisted duralumin at the artillery range, but also a colossal financial sinkhole in the budget of Republic Aviation Corporation. To grasp the scale of this disaster, one must descend from 12,000 meters to the oil-soaked concrete of the airfield. The aircraft's misfortune lay not only in its inability to escape a turbojet fighter. It was completely unsuited for real warfare because of the monstrous complexity of ground maintenance. Each Pratt & Whitney R4360 Wasp major engine required the filling of more than 37 gallons of thick aviation oil. In low temperatures, it turned into a viscous resin. To start the 4 engines early in the morning, mechanics spent hours warming the crankcases with special gasoline heaters. The real curse of the mechanics was the scheduled replacement of spark plugs. There were exactly 896 of them across the 4 engines. In military service, they became hopelessly fouled with lead deposits from the high-octane gasoline after only a few dozen hours of operation. To reach the spark plugs of the rear row of cylinders, tightly squeezed inside the narrow nacelle, mechanics had to dismantle yards of aluminum skin, remove the exhaust manifolds, and disconnect the heavy turbo supercharger lines. The procedure that on bombers took hours here turned into an exhausting multi-day marathon. Military economics never tolerates machines that spend more time in the hangar than in the air. The cost of 1 flight hour of this piston Leviathan exceeded every imaginable limit of the Pentagon. Every time the pilot advanced the throttles, gallons of scarce 115-octane fuel were injected into the cylinders under enormous pressure. The exhaust system, which generated innovative jet thrust, glowed cherry red. The metal of the exhaust pipes, subjected to constant thermal shock from temperature swings between 1,832 degrees Fahrenheit inside and minus 58 degrees outside, rapidly lost its structural strength and became covered with a network of microcracks. Mechanics were forced to constantly replace entire sections of expensive, heat-resistant alloys to prevent the breakthrough of superheated gases straight into the nacelle. Any microscopic leak under pressure in this cramped, overheated space guaranteed an instantaneous volumetric explosion. The designers attempted to solve this fatal problem by installing layers of heavy asbestos insulation, but every new pound of protection ruthlessly consumed the aircraft's useful load and irreversibly shifted the airframe's center of gravity. This was a cruel, closed thermodynamic loop from which there was no escape within the framework of piston technology. For chief designer Alexander Kartveli, the failure of this project became the harshest lesson of his career. He forever realized that the compaction of radial engine installation to reduce frontal drag had reached its absolute physical limit. Further increases in engine power would have required the creation of 36-cylinder monsters, whose cooling would have been impossible. Republic Aviation Corporation was forced to write off colossal losses in an emergency and completely retool its production lines for the manufacture of jet equipment. The very same metal, the same steel rivets, and the powerful hydraulic presses that only yesterday had formed the smooth contours of the XF-12 Rainbow were now used to stamp out fuselages for the turbojet fighter F-84 Thunderjet. This new combat aircraft was entirely devoid of the elegance of the great reconnaissance plane. It consumed kerosene in alarming volumes, but its engine contained only one massive rotating component instead of the thousands of moving parts in a temperamental piston engine. It was considerably cheaper to produce in series, far simpler to maintain in the field, and flew at 560 miles per hour without any problems of cylinder overheating, because massive cylinders no longer existed in it at all. The story of the piston-powered masterpiece, which proved too complex for its harsh era, ended irrevocably. The United States of America was inexorably entering the Cold War, a global conflict that demanded the mass production of simple, reliable, and maximally undemanding weapons. The XF-12 Rainbow was the complete opposite of this concept. It represented an incredibly expensive work of engineering art, too costly to replicate and too delicate for forward airfields. Its creation had been a mistake in strategic planning that cost the nation millions of dollars, thrown irretrievably to the wind in pursuit of an impossible mathematical compromise between aerodynamics and thermodynamics. Yet this colossal aircraft remained an unsurpassed metallic monument to humanity's obsession with speed, a machine that made forged steel, duralumin, and gasoline operate at the very edge of physical possibility. It was an incredibly beautiful, yet utterly hopeless attempt by piston engineering to slam the door loudly before the advancing era of jet turbines. An attempt that burned in the fire of overheated cylinders and dissolved into the lines of accounting reports.